Hello everybody. Today we will start with a spin of an electron. First of all, what is spin? Spin is an intrinsic angular momentum of a particle. What means intrinsic? This means that it is a property of a particle similar to other properties which are specific for given particle. For example, mass or charge. For electron, it is another characteristic of particle, which is this intrinsic angular momentum. And how do we know that this property is specific to electron? It appeared in many different experiments that the only possibility to explain the behavior of electron in these experiments is to assume that it has its intrinsic angular momentum. On the other hand, it was shown by physicist Paul Dirac that this property of electron follows from equations for relativistic mechanics applying for quantum behavior of a particle. So the existence of this property of particles is proved, and we just need to understand what consequences follows from existence of this additional characteristic of a particle. And what are specific properties of this angular momentum which belongs to electron. First of all, we need to state that spin spin obeys usual rules for momentum, and it has its quantum number, and the quantum number for spin is denoted by S, and S is fractional number 1 or 2, 1/2. Consequently, as I already said, that for spin mechanical moment obeys the same rules as usual moment, orbital moment, and so mechanical moment ms is h, and here square root s plus 1. Compare with orbital moment. There was ml was h, l plus 1, the same rule, and quantum number s 1/2. If we substitute it here, if it is s 1/2, we will obtain that it is equal to 1/2 h bar square root from 3. Associated with this momentum is its projection on given axis, and this is the same rule as for orbital. So for ms, z projection on some axis z, we have ms h, where ms is plus minus s and is equal plus minus 1/2. You remember that in orbital momentum m could accept all the values from minus L with step 1 up to plus L. So if S has only two, if we go from minus 1/2 to plus 1/2, we have only one step. So it is then ms is plus minus s. Now let's look at gyromagnetic ratio. If you remember, gyromagnetic ratio for orbital movement of electron, as we derived in electricity and magnetism, we derived that ratio of magnetic moment to mechanical angular moment for electron was minus E over ME, and there was 2. So now in the system which we use, unit system which we use here, we need to multiply by velocity of light. So as far for electron, there is for intrinsic spin moment of electron, there is no 1/2. So it is twice the ratio or gyromagnetic ratio for orbital movement of electron. I already mentioned that for orbital movement of electron we have the same result in quantum mechanics which was obtained in classical mechanics. So this momentum for this ratio of momenta, magnetic to mechanical angular momentum for electron is twice the result for orbital momentum. Here I would like to remind you about experiments which we studied in electricity and magnetism. There were experiments performed by Haas. It was called experiment by Einstein and de Haas, and experiment by Barnett. And if you remember, in those experiments, the result for gyromagnetic ratio was twice that which was expected, because it was expected that orbital momentum is responsible for magnetism, but we already studied that as far as ferromagnetics were used in those experiments, and ferromagnetics, magnetism of ferromagnetics is defined by not orbital momentum but by spin momenta of electrons. You remember these domains which were formed by electrons, which are a region of magnetic with this intrinsic spin momenta oriented in the same direction. Now if we understand that this ratio is twice the ratio for orbital momentum, we understand why the result, how to interpret results obtained in those experiments. So this minus is here because this momenta, angular and magnetic and angular mechanical momenta are directed in opposite directions. So if we look then on from this on magnetic momentum, then we will obtain that magnetic momentum for electron, for spin, for magnetic momentum associated with spin of electron is consequently minus E over MEC and MS. I just rewrite this in to derive this momentum. Now I will substitute it from here, and then we have minus EH over MEC and square root of S plus 1. And this is equal to minus 2 mu B square root of S plus 1. And this, if we substitute what is this when S is quantum number 1/2, So we have minus mu b square root of 3. So mu b is Bohr's magneton, which we introduced when we studied the Zeeman effect at the previous lecture. Again, minus here denotes that this momentum is opposite, this mu s is opposite to this ms. Now, if we look at the projection of magnetic momentum on some axis, so this projection mu s z is corresponding to this relation. We have that it is minus e and mec, and this is projection of ms on the same axis z. And this is equal to minus e over mec h ms, because msz is msh, so I substitute it here. And this is now, if we look what is ms is plus minus 1/2, so this is minus eh over mec and plus minus 1/2. This is equal to, if we substitute what is Bohr's magneton, then we will have minus plus mu b. This is projection of magnetic moment on some axis. Now, if we have two moments associated with electron in atom, look, I do not say movement of electron in atom, because we already know how complicated is this process, that we cannot say that electron moves somehow in atom. It exists in some states, okay? So if it exists in some states, nevertheless, it has two momenta. It has simultaneously has orbital momentum, which is described by L quantum number, and simultaneously it has its intrinsic angular momentum, which is spin. And now, in the previous lecture, we studied that if, for example, we consider two particles with momenta, and we need to know how the resulting momentum is obtained, what is the rule for adding or summation of these moments. The same, we derive some relations, and the same works in the case that we have two momenta associated with one particle. Now we have two momenta associated with one particle, and one of the momenta is characterized by quantum number L, and another is characterized by quantum number S. Then total momentum is mj, and it is determined by usual rule for quantum mechanics. So if we have quantum number j, so it is h j plus 1. Now, what for j, which numbers can it accept? And we know that it can accept if we add two numbers which characterize two momenta and two quantum numbers, L1 and L2. So the possible values are L1 plus L2, next L1 plus L2 minus 1, and so on until L1, L2 minus L1, absolute value. Here, S is only one value, S is equal to 1/2. So it is evident that J can obtain only two numbers, L plus S, and next is L minus S. it is evident that if you subtract even 1, you have already less than this. So you have only this possibility of the first term and the last term in this series of numbers. Here L is orbital or azimuthal quantum number and S is spin quantum number. In the case if we have, for example, L is equal to 0 S state, then J is just S and is 1/2. And if L is not equal to 0, we have that J is L plus 1/2 and J is L minus 1/2. So there are two different numbers. Now let's look what happens in atom due to existence of this splitting of J into possibilities. The total number is different, and we remember that with this mechanical moment, which is characterized by J, there is associated also a magnetic moment, and magnetic moments interact with each other. In this case, even if those two magnetic moments belongs to the same particle, to electrons, they nevertheless they interact, and depending of direction, if these magnetic moments are directed in the same direction or in opposite direction, we have a different energy of the interaction of two magnetic moments. So two magnetic moments, orbital and spin, belongs to the same particle. Nevertheless, they interact with each other, and as a result, this so-called spin orbital interaction gives us different energies depending of number J. So for this value of J we have one magnetic moment, or for this we have another magnetic moment. So if we have different magnetic moments, so this spin orbital interaction between magnetic moments which are spin and orbital, they give rise to different energy, and as a result, each of the levels split, not all the levels, because as if L is equal to 0, then we have only one J, so these levels which are with S state, look here, S means spin quantum number, but we also use this S to denote L equal to 0 orbital momentum. So in this case, if we look at again for sodium and look at the scheme of levels, so here is S, and next is P and S. Column is again, here is n equal to 3, somewhere here is n equal to 4, to 5, 6, etc. And these levels are single ones, because there is only one possibility to J, and for this column, which is P column, and L is equal to 1, so we can have two different columns. One will be for 1 plus 1/2, that is consequently 3/2, and here is 1/2. So as a result, we have here P 3/2 and P 1/2. And this, of course, S is only 1/2. Then the level number 3, with n equal to 3, is split for these two different states, and on energy they have different energy. And if we look on the 4, it is number 3. The fourth level is also split, and so on. And now if we look at spectral lines which are observed, we will see that these lines are also split because these energies are different. And the same is here when we consider these transitions from here, for example. And this was observed in reality, and all these lines are doublets. This splitting of lines due to existence of spin momentum is called multiplicity of lines, and these are doublets. In principle there could be triplets and so on. We will study how it is possible. And in case there are only one line, so it is singlet. So this is just names, and the question arises whether it was observed. Indeed, it was observed in experiments with high resolution. We remember from optics what is resolution. According to Rayleigh, it means that the devices which were used gave possibility to have to resolve even very close located lines in spectra, and indeed it was found in spectra. Moreover, first this splitting of lines was found, and later on it was this concept of spin was introduced. So now we understand that this splitting of spectral lines is explained by splitting of levels, and in turn splitting of levels is due to existence of spin of electron and interaction of spin and orbital momenta, magnetic momenta of electron in atom. Now about usual notation. Usual notation in this more complicated case is that in the center of notation there is a letter which denotes orbital momentum of the level. In the case here will be S, P, D, and so on. So L is the center. Here is J, the total momentum which is calculated. And here is so-called multiplicity 2S plus 1. This denotes how many lines are observed. Actually, here are 2, if we substitute 2s plus 1, and here is also 2. It is denoted also 2, neglecting the case that actually there is no splitting, but this belongs to a series of lines, and so it is customary to denote it with 2 as well. Now we have also to mention that for change of this J, there is also a selection rule, and in all the transitions which happens, delta J should be 0 or plus minus 1. Now let us consider many electron atom with many electrons. If there are many electrons and each of electrons has orbital or azimuthal angular momentum and intrinsic or spin, intrinsic angular momentum or spin, then they have somehow to interact due to associated magnetic moments, and as a result they are coupling in some way and form a total momentum. In the case of many electrons in atom, there are two different cases. First of all, we will consider a case when each of momenta, mechanical momenta ml, of each of electrons interact with other electrons in such a way that all mechanical momentum with azimuthal angular momentum numbers L small, which denotes angular momentum for one electron, for a single electron, they interact in between them, due to interaction between them, they form total mechanical angular momentum mL, where L stands, capital L stands for resultant angular mechanical momentum, and all spin momenta interacts with each other and create ms, where S capital here is. So we have first ml formed ml, and ms small formed ms, this one. Afterwards, this total momentum ml and total momentum ms interacts with each other, and then they form momentum mj, which capital letters we denote momentum for the whole atom as a whole, and with small letters for each of electrons. So this type of interaction between momenta is called so-called SL interaction, or such coupling between L and S to form MJ is called Russell-Saunders coupling. This is most often in atoms, but for heavy atoms the situation is different. This is another case. This is the first case, and this is the second case. And in this case, we have that mLs for each of electrons, they interact with each of ms for each of electron, and they form for each of electron mj small. And afterwards, all this mj interacts, due to interaction between all these mj's, it forms finally total momentum mj. This type of coupling is called JJ coupling, due to first each electron form total momentum mj for each of electron, and then all these mj's interact between them, interaction between them produce this mj. Finally, what we have, if we look at these numbers S, L, large, capital S capital and J capital, then this J can have, due to usual law of summation of quantum numbers, it can have L plus S, L plus S minus 1, etc., up to L minus S. And depending of number of electrons, if number of electrons is even, then S can have all integer numbers from 0 to n 1/2, where n is a number of electrons. And if it is odd, so it is even, and for odd we have from 1/2 to n and halves. So from 1/2 to n1/2. Now let's consider magnetic moment of an atom with many electrons. If we have an atom with many electrons, then for simplicity we will assume that coupling is due to Russell-Saunders mechanisms, and then we will draw this moment of mj, and this moment of mj, mj capital of course, because it is a many electron system, and it consists of two moments. So we have ml, first all the electrons due to interaction produced this total ml, and some ms, and ml plus ms produced total momentum mj. We remember that we can measure only the length of this vector and one projection, but we don't know where actually it is oriented. So we will assume that the system is rotating like this, so producing some average value. So this means that this is the end of this vector in each moment of time is somewhere in this circle. We don't know actually where is it. Now look, with ml there is associated magnetic momentum, and we remember that it is minus, so it is directed in a different opposite direction. And now we will use such a scale that the length in some system of units, artificial system units, the length of vector mu l will be equal to length of ml. Then it is in this direction. This is this vector, and this is vector mu l. So this is in this direction mu l. Then if we look at ms, we remember that this magnetic ratio ms, mu s to ms is twice the ratio mu l to ml. So the length of a vector which corresponds to ms should be twice the length of this ms. So it will be in this direction, it will be twice this length. This is mu s. Again, this directed this way, this is this way. And sum of these vectors produce this vector mu j. Now, as far as all this, due to this rotation, which we assumed will be also here, and as a result, we will obtain some average value of mu, and this average value of mu j will be here due to this rotation. Now let's write down some relations. It is evident from this drawing that mu j, this average value, is equal to minus absolute value of mu l cosine alpha minus mu s cosine beta, when where alpha is this angle, and of course this is as well alpha, and beta is this angle. From the previous part of lecture, we remember that this mu L is force magneton square root of L plus 1, and for mu S it is double the same, but 2 for magnetons, and here is S plus 1. Now if we consider this triangle and triangle for this triangle, then we can derive from the cosine theorem, we can write that cosine alpha is mu j squared plus ml squared minus ms squared divided by 2 mj ml. And for cosine beta we have mj squared plus ms squared minus ml squared divided by 2 mj ms. Indeed, it is easy to see that if this angle is beta, so this angle is also beta. Now if we have these cosines and we have this, for average, we have this expression, so we can rewrite this expression as mu j average is minus mu b square root of L plus 1, and instead of cosine alpha we will substitute this. So for this mj we have j plus 1. The same for L, we have L plus 1, and minus S plus 1. And in denominator we have 2 square root of j plus 1 square root of L plus 1. This was the first term, and the second term is minus. Now we have 2 for mu S, we have 2 mu b, and again we substitute cosine, and we have j plus 1 plus s plus 1 and minus L plus 1, and divided by 2 square root of j plus 1 square root s plus 1, and I lost here, I lost this square root of s plus 1 from here. Now it is in denominator, this is in denominator, so this is this cancelled, this and that cancelled, and we have that this is equal to minus mu p, and here I have a long value, and j plus 1 plus L plus 1 minus s plus 1 plus 2 j plus 1 plus 2s plus 1 and minus 2L plus 1, and in denominator 2 square root of j plus 1. What we have minus mu b, and now we can multiply by square root j plus 1 numerator and denominator, so we put it here, j plus 1, and here in denominator we already have 2 j plus 1, and here in numerator we have 3 j plus 1 minus l plus 1 plus s plus 1. If we calculate what we have, here is 2s but minus, here is minus 2 plus, here is 2 j plus 1 and 1 3 j plus 1. Now we can rewrite this in the following way. We can say that this is equal to minus mu b square root of j plus 1, and here in numerator I will split this first term in 2 j plus 1 plus 1 j plus 1. The first 2 divided by this gives me 1, so it is 1, and the rest is j plus 1 minus l plus 1 plus s plus 1, and divided by 2 j plus 1. Now look, if we compare this expression with expressions for ml and ms, we have a similar result, but here for magnetic moment, this mu j, there is additional factor. So we can rewrite it in the following way, that mu j, which is equal to its average value, average I mean due to this rotation which we assumed, this is minus mu b and some factor j, and here is square root of j plus 1. This g is called Landé factor. It is this factor here is due to double magnetism of spin momentum. Now look for different cases. For example, if we have total L equal to 0, then in this case J momentum is equal to S because L is 0. Then in the numerator here we have 2 j plus 1, in denominator 2 j plus 1, and this gives us 1. So here we have 2. So in the case mu j is conditioned only by a spin momentum, we have twice momentum of mu b. Here is coefficient 2. So g is equal to 2. And imagine that somehow all the momenta when they were added produced total momentum, spin momentum of atom equal to 0. Then J is defined by L, so L and J is equal, so J minus J gives 0, and so here is 1. So if the momentum, magnetic momentum, is conditioned simply by orbital momentum, then here is 1. So these two different cases. One case when all the momentum is only by L, defined only by L, gives us this single magnetic momentum F, and if only by S, so twice the magnetic moment. This G is 2. And in the general case, when both L and S defines J, so this G lambda factor has some intermediate value between 1 and 2.